And okay, remember, clean start, clean end, good look.
Yeah.
And we are okay to go.
Go. Good afternoon. Welcome to UniCourse. This is a presentation on Unit 20, Digital Principles, and we're going to be doing Assignment 3, Hints and Tips. At the end of the session, what we're going to do is have time to do a question and answer. So first, let us go through the criteria of this assignment. What you can see on this slide is what are the various criteria. And what is important is to look at these criteria as well as look at the actual tasks you need to do. So the first one is apply lab equipment to describe and evaluate simple digital circuits. Apply lab equipment to configure and test simple digital circuits. For the second part, apply lab equipment again, test and evaluate digital circuits, comparing and evaluating characteristics of different technologies. And this is what the basis of the assignments can be around for the passes, the merit, and the distinction. So we're going to look at again and look at holistically or the overall part of each question. Well, we're going to through it again at the end and different theories throughout this presentation. So apply lab equipment. Now it does say lab equipment. This is going to be where you'll be using the simulation side, which I'll go to in more detail. And what you'll be doing is simulating your choice to build a TTL, a transistor type logic, an up counter, and a 3-bit SIPO series in and parallel out. So it's series in, parallel, register. And then it's only a few questions in this one. That's why we're on to the merits. We apply lab equipment to configure and test digital circuits. And this one is where we're going to look at the maximum usable frequency from task 1. So some further tests to carry out. And the final one is looking at evaluation and comparing. So what you'll be doing with that one is build 2 more circuits, but this time using CMOS technology and comparing it with TTL, transistor type logic versions, and see how they work and how they compare. So let us look at an introduction to circuit simulation. As you know, you have been provided, you've got microcap and Tina. I've been looking at a few other simulation packages that you can use. And here we have a circuit here, this counting circuit here, which can be produced on most of the simulations. Now the Tina one, we can't use for this logic because it's only an evaluation one, unless you buy your own version. But all other simulators we're talking about today, you'll be able to do the logic. The Tina, that's the one which is good, it's free, but it doesn't have a digital library. The main Tina one itself, so you can, but you have to pay for that one, which is up to yourself, and that does have both analog and digital simulation. So in the library, it's well provided. And Multisim, that is a fantastic package, industrial standard. You can download an evaluation copy. It is quite a big one. It does take a lot of time to download it, but you've only got 30 days and then have to buy a copy of it. So it's a nice one to use, but it is, unfortunately, you have to pay for that one. Circuit Wizard is another one. That's when you can go on their website. It's very easy to use, and the license for that one's cheap. That is well under £50, or has been. And the one which I have been using recently, which covers a lot of the areas, is Circuit Lab. This is an online simulator. You can use the evaluation one, but it'll time out just after about an hour. but it's very similar to one or two. The other one I haven't put on here is microcap, which is the one which we use a lot of here at UniCourse. So we'll look at some examples now. This, if I'm right, is the microcap one. You can see the transistor analysis. It's very in depth, and we can see here the waveform here. This waveform we call the timing diagram. And throughout this assignment, we'll be looking quite a lot of these. And it's important when you create the assignment, if you are looking at logic, to produce the actual circuit here, annotate it, which I'll go to in a bit more detail, and then include the waveforms. And it's not waveform, it's waveforms. And you can see here the pulsing waveform, and at the different stages, I can see how the clocking mechanism in each one times, and you can see the square waves working from there. So let us go on to another one. This one is Circuit Wizard. It's quite an easy one to use. It's got an extensive library in the analog and digital. What you've got here, which is the logic analyzer, you just connect these up directly to the Q outputs, and then you can produce a timing diagram like this. It's in different colors, and you can expand it, and it's a very nice package to use, and it's not too expensive. So that's one to consider. But I say there's no evaluation version for this one, which you can just use. So that is another one to consider. Another one to look at is one I have been talking about, which is Circuit Lab. They have what you call, with the online package, a library of pre-produced circuits. Some of them being produced by people who've actually bought the package, and the creators of this package have also created. And there's various textbooks that go with it. So if you Google it as well, you can look at it. There is also various video tutorials that they have as well, which are on YouTube. And what also you get with the package is a timing diagram. I would say the analog is probably more, there's a lot more than live in the digital, but they are building it up. It's a new one I've only recently seen, but every time I open it up, I see another circuit they've added to it. So it's worth Googling. It's known as Circuit Lab. It's a free up to about an hour. They do a student version, which is around about £30 a year. You don't buy it. Once you bought the license, you have to renew it every 12 months. A bit like having Office 365 and things like that. But the good thing about it is it's quite easy to use. There's a lot of sample programs, and a lot of our learners are starting to use this one now. But it's microcap is the best one. But if you are not as techy, then things like Circuit Lab is worth considering. Now, I mentioned earlier on that we have TTL and CMOS. TTL was probably historically the first one was developed, transistor type logic, and the first type of logic circuits to develop after the thermodynamic valve was using transistors. But back in the late 1960s, early 70s, companies like Texas and a few other semiconductor companies who were making the diodes and transistors and thyristors were starting to producing logic gates, and TTL. And we can see here on this table here, if we drill down, what we've got is that it's a 5 volts plus or minus 0.5. Admittedly, when I've used TTL, I've got up to about 10 volts. I think if you go down to under, say, 3 volts, it won't operate. The logic won't operate. Flows high to logic 1 if unconnected. In other words, if you've not got right grounding with it there, it will go to its own state. So it's important. I know when I was working on logic circuits a few years ago, when I was checking them out, if there's nothing soldered properly on, you would get this floating high. 16 milliamps to sync it, that's enough to be able to create, to get it to use it through a drive an LED, and the LED is also about 2 milliamps. The fan out, that means to say is how many you can drive. You've got 10 logic gates, or in the HCCT, 50. And the frequency, as you can see from this here, is around about 35 megahertz. And what is important, and I'll discuss this in a bit more detail, is that as we can see, the power consumption is in milliwatts. Now that doesn't seem a lot, but I'll explain when we look at the next one, the CMOS range. So the 7.4 and the 7.4HS, high speed, 2 to 6 volts, has high input impedance, has, without, you don't need a pull-up resistor as well for the logic. It can sing up to 20 milliamps, enough to light an LED. You can have 50 CMOS inputs and one about 10 inputs. And the speed, the maximum speed, is around about 25 megahertz. Now, can you see this here? The actual power consumption is a few microwatts. Now that is very, very important, because in today's electronics, and I'll give you one very simple example. When I bought my first digital camera around about 2000, the amount of batteries I had to use after taking a few shots, especially when I did flash. Soon as we moved over to using the CMOS side cameras, and of course our mobile phones today wouldn't work as well, they wouldn't last as long, the power wise, it wasn't for the fact that the technology is probably something more advanced than the CMOS, but it probably only uses microamps, and the power consumption is probably a very few milliwatts. If we look at the next series here, 7.4 HCT, 5 volts, 0.15 volts. So in other words, that's a power supply, high input impedance, compatible with the 7.4LS range, sinks around about 20 milliamps, enough to drive an LED, and one output can drive about 50 CMOS inputs and about 10 7.4LS inputs. And the frequency again is 25 megahertz, which is the same as the other one. And of course, the wattage is low, which makes the current will be low as well, so they're ideal as well. But in the old days, using CMOS technology, and to a certain degree today, when you were using it as a construction or you're replacing it, they were prone to static, so you had to make sure you earth yourself, where the TTL is a lot more robust, and it doesn't matter if you touch it without earthing yourself, you shouldn't cause any damage. But these CMOS series at one point, they're probably battery built now, but they used to be, if you touched them with your fingers, they would blow and you couldn't use them. So that is the family of the TTL CMOS series. And we'll just go into the what they're saying, the fan in, that's a maximum number of inputs to a device before it becomes unreliable. The fan out, number of output connects to other gates before it becomes unreliable. Propagation delay, that's the speed it takes, the time that the low to high transitions, and we'll look at that on the counters, and power consumption, and that's important. And when the chip designers, or when the designers of electronics in general are looking to build something, they will take a lot of this into consideration, and they can consider what they're going to use, either TTL or CMOS. Now, if we drill right down and look at it in the transistor side, we can see here there's two transistors, and this is a TTL inverter, which is what we call in the trade as a NOT gate. And then we have NPN transistors, and the NPN transistor Q2, Q1, there's the output, and the base is connected to the 5 volts. And here we've got the collector going to, and this drives the output. So this here, a common emitter, which the input comes to here, and there the output will be switched over here to the output, where on the CMOS inverter, like a FET, So the input there, this will drive the output of the FET, the drain, and that will be through the resistor there, and that output there, and that CMOS will convert it from either a 0 to a 1 or a 1 to a 0. And that is why we call them inverters. So let's look at counters, and I've brought this up in last week's presentation. So we've got parallel in, parallel out, parallel in, series out, series in, parallel out, and finally series in, series out. And of course, all of these have their own uses in depending what sort of industries you want to use them in. So we are going to drill down and look at one or two of them and look at how the circuits operate. So here's one in the series in, parallel out. Okay, so what we've got here is the clock here to clock each one of these SR, as you can see here, and then there's a diode there to stop it from not going the wrong way. And as we flip it over, it'll go Q, not Q, and you can just carry on here. And you can see here where the output. So you've got a series in, which will be coming in from a series of input pulses using the clock here to move it along. And if you look at the timing diagram here at the top, and we can tell that this is a clock because of the frequency. And as we move down, it only gets driven by the waveform that's going up, the rising of the waveform. And each time we have to wait for the next one, and that is then divided again until we get to 1. So this is the timing diagram. These can be connected up to LEDs or some form of indicators. And that's one of the shift registers. And what is important when you're answering the question is besides using our UniCourse workbooks, which are excellent, is to do some further reading. And there's some very, very good web-based resources which you can use. And if you're using either web-based resources or UniCourses, make sure that you harbor reference them and that you've got everything annotated and you put citations and where you've got the information from. We will be looking at that a bit later on in this presentation. So we'll look at counters now. And here's a 4-bit asynchronous up counter. There's a clock. You can see going up there, and as we go. And the reason why we've got Q0, Q1, Q2, Q3, these will be connected through another buffering device, and that can be connected up to a display. And if you add up to 7, you can have a counter which would count from 0 to 9, and then we reset again. So we start at 0, 1, 2, 3. Here we've got the clocking frequency, and you can see it clocks at 100 hertz, and this is how it's counted. You can see the relationship between the two here on the left and right. Don't forget, when you include these in your assignment, don't forget to include the clocking timing waveform as well. So we'll look at one here, which is series in, parallel out. Okay, SIPO. It's a 4-bit data bit shifting by the 4 clock pulses by wired data in, got the clock, the data in. You can start to see a commonality on it and how the outputs are. This is a block diagram version of it on the top, and then we can see how it electrically is connected up. And these 4 could be all in one chip. You can have 4 in line, and then the wiring have to be then configured. So you've got the wire to connect up to your clock, a reset, which is clear, which is like a button, and then there's a data cable in to provide the data in, and that's how it will work. So that's the one chip. Okay, so we've got here now the series in, parallel out. That's using a 74AS64164A. Now you'll find that if you look in the library of these simulators, and usually I know that I know on Circuit Wizard it's on the right side, and you right click the actual IC, it will bring down different manufacturing types, and there'll be there you can decide which one to want to try out, and then connect it up. So this is a series in, parallel out, 8 bits. It's all different time. You can then, if you want to, you can just Google this and look at like the Texas or whoever manufactures this this IC, and you'll see quite a lot of information, which including the fan in, the fan out, the speed, propagation, a lot of manufacturing data, and that can be very useful. And it's used a lot by the design engineers. Usually they'll simulate it first before they then build the first prototype using proper hardware. Now, we mentioned this last week, but what's important that when you're using these counters, these shift registers, that you've got to stabilize crystal weight as an oscillator. And using the crystal oscillator is a very stable way. But one disadvantage is that with the crystal, it will be fixed a frequency, where if you're using, for example, like a Wien bridge or some other Schmidt triggers, 1 or 2 other oscillators, you can change the frequency to suit what you would think will be suitable for that chip, for that IC. We'll look at some more counters. Okay, this is a shift counter, a temporary storage device, digital devices for data. You can see on your left-hand side this information here. Can be used, which we'll be looking at next week. We're looking at adders, used for digital arithmetic, for operations such as multiplication and divisions. And so the calculators of today would use something like this, but they will be built in a large chip using quite extensive large LSI, large scale integration. But if you look at the circuit diagram, you probably just about make out these shift counters. And here we have a shift counter here to our right. As you see, we move along here, moves along the data, but we can plot the data as it moves along to the actual output. And the clock is over here at the bottom side. All right, we're sort of halfway through, or probably more than halfway through now. We're going to move a bit more onto the background, the theory of this assignment, and then we'll be doing the hints and tips of completing this assignment 3. Now, one of the questions, which I'll let you decide which one it is looking at the maximum clock frequency. And that is important, that if we want to work out what that IC that logic can take, and I've taken just a description from one logic chip, and here is one here, and we can see to our left that we've got up to about 72 megahertz. You could try it out by changing it on the simulation, and you can see if it affects on the timing diagram, and see if you can see what sort of waveforms you're getting on by putting the frequency. They're not just a couple of hundred kilohertz, but if you whop it up to about 70 up to 100 megahertz and see what happens. And you need to be able to document that down if you're looking at doing that question, which is one later on. And here we've got another one here, and you can see here the clock impulses here, and to the right, it's a bit of a data sheet here where you've got the maximum clock frequency, minimum pulses. So the design engineer will be looking at this very closely if they need to be looking at electronics that need to have high speed, especially when you're looking at control systems where they've got the little computers, the CPUs, working at very high frequency. Now, we're going to look at some of the questions and some background to completing them. So we're looking at using an electronic simulator to build a TTL 0 to 3 up counter. What I would do is first thing is look at the UniCourse study guide, see what is in there. Even if you find things like a 4 or an 8, you can actually slim it down to a 3-bit. And then you need to start constructing it using one of the recommended simulators, which can either be microcap. You can use, you can't use Tina for this one. You'd be able to microcap. You can use Circuit Lab, Circuit Wizard, and Multisim. So, but a lot will actually go for using it with microcap or the Circuit Lab. Then you need to build series in parallel out shift register. Don't forget to have your timing diagram, which is on the right, the actual schematic drawing of the actual what you're actually going to use. Don't just cut and paste it from. I think you need to have it built using a simulator. You need to look at determining the maximum usable frequency. That needs to also be using a simulator as well, and the suitable clock oscillator and decoupling the noise. That is one to do, which is for another section there, which is not for this one. And then, of course, the final part of the question is the CMOS logic. So you're doing a comparison with CMOS versus TTL. So look at the that slide early on, and then you need to actually build a circuit from task 1, which is the up counter and the 3-bit SIPO, using both CMOS and TTL, and then looking at the results, which you need to show evidence, screenshots of, and I can see all that for marking purposes. And don't just use screenshots from other ones. We need to see that they are from the ones that you built yourself. So that's just a couple of things that hints and tips. When you're setting out the assignment, use both the UC, the UniCourse study guides, and further reading. Make sure that your diagrams are annotated, explain how the circuit works. So you've got the circuit with it, and then just put some information about it, and you'll document that. And on the right-hand side, usually you will have the timing diagram. And of course, hard referencing, you need to make some reference actually on the section that you've taken it from. The diagram, or in this case, it won't be the diagram because you'll be building these using the simulator or any other documentation. As you can see, is an example of how I like to see it. This is from using Circuit Wizard. We've got here the logic analyzer. These will be part of the simulator, but you can see that I've actually put the clock pulse and the flip-flops and the timing diagram. If you do something like that for your actual simulated screenshot, you're on the right track. Right, this is coming to the end of the presentation. So, have you got any questions? Right, I will say thank you, bye-bye. Next week, we'll be looking at the final one for this program. Thank you, bye-bye.